All right, we're going to look at operations with vectors today. We're going to look at them geometrically, which means literally the picture of the vector itself, and then also numerically, okay? All right, so when you multiply by a scalar, okay, a scalar is just a number. Scalar multiplication is a phrase that you may have heard before. It is going to be, a scalar is a real number, usually a lowercase k. Called a scalar. It will change the magnitude of the vector. Remember, the magnitude is the size or the length for our purposes right now. If k is negative, then it causes it to go in the opposite direction, right? So here's a couple little examples. I mean, it's really kind of should make total sense. So here's vector v. Remember, the vectors can be anywhere. We don't know anything about location. So 2 times vector v is going to have the same angle. It's just twice as long. Half of v, same angle, half as long. Negative v, same angle, just going in the opposite direction. Okay, well, actually, it's not the same angle. It would be a different angle. Obviously, this would be a first quadrant angle. This would be a third quadrant angle. But the length is the same. It's just going in the opposite direction. Okay, does that make sense to you on that? Okay. So then we add them. Geometric representation of addition, v and w, is shown at the right. They're positioned so that the tip of v coincides with the tail of w. When you add them, their sum is called the resultant. So we have a resultant vector. So here's vector v. Remember, you can move them around. Move them around in any spots. So v is right here. Wherever v ends, then that's where w is going to start. You just kind of connect them together. Think like snapping Legos or something together. And then here's v, here's w. When you connect the two, that is your visual representation of v plus w. Okay. Then when you subtract them, the difference, so if you do v minus w, it's really v plus negative w. That's how you know it goes in that opposite direction. And it's using the same tip to tail model that's shown above. Okay, so then here's vector v. It's the same as this one right here. The difference in the w's is that this is negative, so it's going in the opposite direction. But notice it still starts right here. It just goes this way. So then this is your v minus w. Okay, we good? We just kind of can move them around and snap them together. All right, so when we look at this numerically, if vector v, remember it can have the little arrow over it, vector w, and it doesn't have to because it's bolded, but either way. We have vector v, vector w. Vector v is a1, b1. Vector w is a2, b2. So scalar multiplication, when you do k times vector v, it can look like this. K times v is a1, b1, and which would give you, when you multiply it, it gives you k times a1, k times b1. You literally just multiply it by both of them. It's as easy as it sounds. When you add them, it's like adding ordered pairs. You add the two x values, so we've got a1 plus a2, comma b1 plus b2. And you can add in any order, so if you mess that up, it's not the end of the world. Just don't mix your x and y's. But when you subtract, you got to make sure that you are going in the correct order. So since it's v minus w, you take the x value for v, which is a1 minus a2, and then b1 minus b2. And like I said, it's as easy as it sounds. There's no tricks there, you know. Any questions? We good? All right, so then on number 1, 2 times vector c. So they give us an a, b, and a c right here. So 2 times c, we could write it as 2 times negative 4, 5. So you might see something like that. That's the one the scalar's on the outside. But then you literally just multiply it by both. It's going to give you negative 8, 10. C minus b. The x value for c is negative 4 minus the x value for b, which is 1. Then 5 minus 7, which means I'll get negative 5, negative 2. We good? Make sense? All right, so then a minus 3c. X value for a is -6 minus 3 times the x value for c, which is -4. You just do it all together. And then the y value for a is 2 minus 3 times the y value for c, which is 5. Everybody okay with where all the numbers came from? Make sense? I mean, you can do it in more steps if you want. But so this is going to give me a positive 12, -6, so that's a positive 6, -15, positive 2, -13. Any questions about any of that? All right, so on number 4, there's a fraction bar missing. So put in that fraction bar, and then you do number 4. -4, -6? Yes? Any questions? All right, let's flip it over. All right, so then we have something called standard unit vectors, which is going to give us a different way, a different form to write vectors in. So your standard unit vectors are always called I and J, and they're always the exact same thing. They could be called I and J and just be bolded. They could have the little arrows over them, but they could also have these little, what they call hats on them. Now my pen makes it look curvy at the beginning when I do them small, but it's like the caret top you use on the calculator to make an exponent. That's what the shape is that I'm trying to draw, but I seem to get the little hook on it every time, even when I'm not trying to. So you can put them. So we're gonna, just for the purposes of letting you see the different stuff, you call them I hat and J hat. Okay, or it can be the unit vectors I and J, but we'll call them I hat and J hat. And it's a unit vector, meaning one unit, along the x-axis and along the y-axis. So I is the x-axis, J is the y-axis. So I hat is always 1, 0. J hat is always 0, 1. And then we're going to use those to form what is called a linear combination of vectors I and J. So any vector v, which is in the form of AB, can be written in the form v equals a I hat plus b j hat. And I'll show you how that works and why it makes sense, even though it seems a little strange. Okay, so we're going to go through these 3 steps. You do not have to do these steps every single time. The steps just show you why it works. Okay, so we're going to rewrite this vector as a sum of 2 vectors. So I can rewrite this as a comma 0 plus 0 comma b. Would you agree that that's the same thing? When I add them together, I get vector AB, right? Okay. So then the next thing we're going to do is we're going to factor out a and b. So if I do that, then I get that vector v is equal to a times 1 comma 0 plus b times 0 comma 1. And if I were to go backwards and multiply the a and the b back in, I'd end up back at step 1, and then I can add those, and I end up back at the original, right? Okay, so then what is the vector 1, 0? It's I hat, right? And 0, 1 is j hat. So when you do that and we substitute that in, This becomes I hat, this becomes j hat, so that gives me a I hat plus b j hat. And that's why that they are the same thing. So instead of so you have component form, which is the pointy bracket form, and linear combination form, which is the I hat, j hat form, right? Given the component form, linear combination is super easy. Because like I said, we don't have to go through those. We could, but we don't have to do that. That was just showing you why it works. Bless you. Vector v, this is component form. Linear combination form would just be 2 I hat, bless you, plus 5 j hat. And it's that easy. That's your answer. Okay? And it kind of depends on what you're using it for, what forms you might want it in, even though it seems strange, like why would I want it in that form? Eventually you'll see that. Just we gotta look at the different forms right now. We good? So that means that number 2 for vector n, that should be super easy, right? It's just negative 7 I hat plus 3 j hat. So converting forms, piece of cake. Now on number 3, they give me the initial and the terminal point. They don't give me component form. So I want to put it in component form, and then I can easily get it in linear combination form. So vector rs, okay, and remember, the order in which you do things make a difference. This is your initial point. This is your terminal point. So this is initial, this is terminal, which means we do negative 5 minus a negative 9, which gives us 4, and then negative 6 minus 8, which is negative 14, right? So that's component form. Linear combination, which is what they asked us to do, is then going to be 4 I hat minus 14 j hat. Any questions about that? All right, then you do the last one. And just like with variables or other things, if it's a 1 and you have something there, you don't have to put it. If you did put the 1, it does not make it wrong. It's just you wouldn't see it in that form. So you should get 8 I hat minus j hat. We good? Any questions? All right.